Hello, I'm Jung Peg. You're in the computer architecture course. We're continuing our discussion on chapter 5. So far, we've talked about the memory hierarchy. We've talked about caches. We talked about the design of cache, how cache works, how important caches are for performance, and so on. Okay? So far, we've mainly been talking about CPU, cache, and memory. Okay? Now we're going to go one level down. Okay? So far in our discussion, we've been talking about CPU, main memory, and cache. Okay, and we've talked about how cache helps main memory. Cache is just helping to improve the access to the main memory. So cache is just a helper to make the performance better when the CPU tries to access the main memory. So this is just for performance. So let's just forget about cache. Okay. Now let's just forget about cache. Just focus on the main memory. Okay. So let's say we are running some program, your program. Okay. So let's say your program is here. This is your program. Okay. Your program is in the main memory and you're running your program. So your CPU is running the program. How do you run the program? You're running instruction by instruction by instruction. You're running your program in the memory sequentially. We talked about this. Okay. Running a program means moving in the memory. Okay. Of course, we might do branch or we might do jump and so on. And we might access data here and here and here, but still you're moving inside the memory. Okay, that's how you run your program. Okay, we run instruction by instruction by instruction. Okay, and those instructions get executed in your pipeline in your CPU. Okay, so we've talked about all of this, but so far we've been assuming that only one program is running in your computer. Okay, so far we've been assuming that there's only one program in your memory. Okay? We've really never talked about what happens if there's more than one program. Okay? So let's look at that problem now. Okay? Multiple programs. I want to run more than one program. I mean, if we think about computers in the 1970s or 1980s, back then, only one program was running at a time on your computer. Okay? So your one program can use the whole memory by itself. Okay, but these days, who runs one program? I mean, on your operating system, there's multiple programs running, always multiple programs running at the same time. We run like 10, 20 programs or processes at the same time. Okay, so multiple programs want to use single main memory simultaneously. Okay, I mean, we do this every day. Okay, we have only one main memory, but I want to run many, many programs at the same time, multitasking, right? So what if program A wants to use some memory address and program B also want to use the same memory address? What happens then? Okay, I mean, your program, let me, okay, your program is running here, but at the same time, you want to run a second program. And let's say that second program is also using the same memory address. So we have a problem. Okay, we cannot do this. This is impossible. Okay, so what can we do? If multiple programs run at the same time, okay, I want to share the main memory. Okay, so and the same problem, there is a same problem when running two instances of a same program. Meaning, you know, when I open two windows of PowerPoint, or when I open, you know, 3 windows for a web browser, we do that, right? We run several instances of the same program, and we have the same problem. Okay, if I have a single program and if I run multiple instances, they will use the same memory space. Okay. So we have a problem. Okay, so if you think about it, all of these refer to the same problem. I want to run more than one instance of a program on your computer. They have to run from the main memory because running a program means moving in the main memory. How do we do this? This is one problem that we need to solve. There's another problem, okay? Program A wants to use 2 gigabytes of memory, but my computer has only 1 gigabyte. What can I do? Okay? You might have a computer which has only 1 gigabyte RAM, but my program needs 2 gigabyte. What happens? Will it crash? Okay. I want to run same program on different computers with maybe 4 gigabyte, 2 gigabyte, 1 gigabyte, whatever, maybe 512 megabyte of memory. Okay. I mean, I have a program. I want to run this program, but I want to run this program on this computer. I also want to run this program on this computer or that computer or that computer, any computer. Okay, but this computer might have 4 gigabytes of RAM. This computer might have 1 gigabyte of RAM. This computer might have 512 megabytes of RAM, but I still want to run the same program. Okay. I mean, should this happen or not? Of course, this should work, and this works. I mean, you know it. Okay. Of course, if you have different sizes of RAM, it's going to be the performance will be different. Sometimes, I mean, if you have small amount of memory, it's going to be slower. If you have big memory, it's faster. You know this. I mean, even if you don't take this computer architecture course, even if someone does not major computer science, okay, they know. We know by experience that if you have small RAM, it's slow. If you have big RAM, it's fast. We can feel that. But why and how? What's going on? Okay. I want to write my software without knowing the memory size. When you write software, do you care or worry or think about how much RAM you have on your computer? You don't. No, I don't want to do that. Okay. When I write my code, I don't want to worry about whether I'm going to run this on a 1 gigabyte computer or 4 gigabyte computer. Okay. Different computers have different RAM size, but my software should still run, right? I want to write my software without knowing the exact memory address. Okay. I mean, when I write my code, I don't want to worry about, hey, memory address 0x8008FF. I don't write that. Okay. I mean, we just use pointers and references and variables. We don't really write the memory address directly. We never do that. Okay. So this is another problem. Okay. When I write my software, I don't want to worry about the memory size, and I don't want to worry about the exact memory address. Okay, memory size, exact memory address, I don't want to worry about that. Okay, so we have these two problems which we don't know how to solve yet until this point. Okay, and now we're going to discuss how we can solve these problems. Okay. Okay, so let me draw some pictures to clarify this more. Okay, so let's say I have this program A. Okay, I have this program A. Blah 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 blah. I also have this program B. Okay. In this program, I mean, this is the amount of memory that each program uses. In this program, we have the text area, the static data area, the heap area, the stack area, all these stuff, okay? And, you know, when we run the program, our instruction will run sequentially. We might branch, we might jump, we might use data, whatever, but we are still within this space, okay? And then we have the main memory, okay? We have the CPU, okay? We might have some cache here that helps improve the performance of our memory, but let's not worry about cache now. Okay, let's just focus on the main memory. Okay, I want to run both program A and program B on my computer. Okay, but if all of them comes to the same space, then we have a problem. We cannot do that, right? So when I run program A, it should run somewhere here. Let's say program A. And if I run program B, it should run somewhere else. Let's say here, program B, okay? And I don't want to, you know, specify the exact address because I don't know which program I'm gonna run. I don't know how many instances of the program that I'm gonna run. I might run A first and then B, or maybe B first and then A. I might run A, B, C, D. So the location in the main memory can change, right? First of all, you need to understand that. Then let's step back and think about how we run the program. Where is this program? Okay. Well, before running the program, your program is actually in your disk, your hard disk. It could be SSD, but still, same thing, okay? It's actually in your disk. Your program is in the disk A, okay? I have my program A and program B in the disk. Now, you want to run the program. What do you do? On Windows, you double click. You double click to run a program, or maybe, you know, you type a command, you know, run program or open this program. When you do that, when you double click on a program to run it, this gets copied into the main memory, from the hard disk to the main memory. What do you call this procedure? You call this procedure load or loading. Okay? You load a program from the disk to the memory. Okay? And it has to be in the memory so that the CPU can run it. If your CPU wants to run your program, it has to run from the memory. Okay? And again, cache can help improve the performance, but that's just helping to improve the performance. Okay? Fundamentally, it's not changing the behavior of how you're running it. Okay? So cache is just a helper. So just forget it for now. Okay? Your program was in the disk. When you run it, it gets loaded into the main memory and you run it. Okay? Where in the main memory should it get loaded? Well, it has to be dynamic because we run multiple programs. We do multitasking. We don't know the order or sequence or how many programs we run. So it could be anywhere, but we have to decide. Let's put it here and then run it from here. Okay, that's one thing. Another thing. Okay, we talked about on the previous page, we talked about, I don't want to worry about the memory size. I don't want to worry about the memory size. Okay, my program might need 2 GB, but my computer might have 1 GB. We talked about this, right? So let's say my main memory is only 1 GB. Okay, but my program could actually be much bigger. Okay, up to how much? Up to. What is the maximum size of my program? Well, on a assuming 32-bit computer, assuming 32-bit computer, okay, which means 32-bit memory address. Okay. If we assume a 32-bit memory address computer, then the maximum size of my program can be how much? We've learned this in chapter 2. In chapter 2, what is it? 32-bit. 32-bit means 2 to the 32 bytes because memory address is byte address. Okay, this is what? 4 GB. So the maximum size of your program, or the maximum memory that your program can use, could be up to 4 GB. Okay, maximum size of your program can be up to 4 GB. But we only have 1 GB in your computer, in the real physical memory. Okay, physical main memory. Okay, I only have 1 GB. I'm poor. I don't have money. Okay, so what can I do? Okay, so in the hard disk, I have all of that. I can have up to 4 GB here. Okay, I can have up to 4 GB here. Okay, but when I load it, let's say I cannot load all of it. So let's say I've only loaded this much, okay, which is just this much. Okay, so the remaining part, this whole thing has to stay here, right? Let's say this is this, okay? Then this remaining part, I cannot load it to the memory. I don't have enough space, okay? Then what can I do? Well, we're going to use the same concept as the caching, okay? We're going to put, so we're loading something, but there's something that we cannot load, so we have to put it back here. We have to put something here. okay? Which means we're using the hard disk as a fake RAM, okay? We want to use the hard disk as a fake RAM, okay? So in your hard disk, there's this space. There's this space which is like fake main memory. Okay? Fake main memory means I want to put this in the main memory, but I don't have enough space. My memory is small, so I temporarily just put it on the side in the hard disk. Okay, and this space in the hard disk, okay, which we use as a fake main memory, we call this the swap space. Okay? Fake main memory, or something that we have to put in the disk because my main memory is not big enough. Okay? Same thing when I run program B. Okay, I want to run program B. My program was originally here, and I double click on it. I want to run it. So you load the program. You load the program. Okay, but my physical main memory is not big enough. It's small, so I can put only small size here. I can put only small size, maybe just this much. So this part I cannot put, so I have to put that here. I have to put some here in the disk, okay, in the swap space, which is like a fake RAM. When I run the program, I have to copy everything. I need to load everything to the main memory, but I have only small RAM, so I have to put some other things in the disk. That's called a swap space. Okay? So that's that. Let's go back to this question. Where is it? Multiple programs want to run single main memory simultaneously. What if there's a conflict in the main memory address? I want to share the main memory and so on. Okay. So here, you know, I'm running my program A like this. Okay. And there's some main memory address that I'm using. Okay. But obviously, when I copy this to the main memory, when I load this to the main memory, I don't know where it is. It could be anywhere in the main memory. Okay. Right? This could be anywhere in the main memory. So I don't know the real memory address. Okay? So now we're going to separate out the memory address space. Okay? Memory address or memory address space. Okay? So far, you know, we've been talking about memory address. Okay? And the total memory address, that the space that we can have. What is the maximum memory address space we can have? Okay, if we have a 32-bit computer which has 32-bit memory address, 4 GB is the maximum space that I can have, memory address space. Okay, now, but the memory address space of these programs are actually virtual memory address space. So program A is using a virtual memory address space, okay, of 4 GB. Program B, Program B also has a virtual memory address space of 4 GB. Okay, it can use up to 4 GB. Program A can use up to 4 GB. Program B can use up to 4 GB. That's all virtual memory address space, okay? But our real memory address space is where? This is our real memory address, the physical memory, okay, address space. And physical or memory or real memory, I have only 1 GB, okay? So I cannot put everything in the virtual address into the real memory, okay? So I need some translation, okay? And so far, I've kind of simplified everything, but let me just clear this up a little bit. Oops. Okay. Let me clear this up a little bit. Okay. Program A, we are talking about program A, and let's say, we're not using all 4 gigabytes. This is program A, okay? And program B also, we're only using this much. So let me just color this up. Let's say this is program A. This is program A. And this is program B, okay? So in the hard disk, we have program B here. And we have program A here. Okay, it's not using all 4 gigabytes. So let's say, program A uses maybe just 2 gigabytes, and program B uses just 1 gigabyte. Okay, so program A uses 2 gigabyte, program B uses 1 gigabyte. We load it. We load the program. When I load program A, I don't have to put it at one space. I can put a little bit of program A here, little bit of program A here, little bit of program A here, okay? And when I load program B, okay, I can put a little bit of program B here, a little bit of program B here, a little bit of program B here, okay? And whatever that does not go in, I can put it in the swap space. So I told you this is the swap space. And I can put some of program A here and some of program B here. Okay. So when I'm running a program, let's say program A, when I'm running program A, in the virtual memory address space, it feels like it's running like this. Okay. But in the real memory address space, you might run it here, and then here, and then here, and then maybe I need to copy something up here, and then here, and so on. When I'm running program B, okay, in the virtual memory address space, it's running like this. Okay? However, in the real memory, okay, it's running like this, and then this, and then this, and then maybe copy this up here, and then here, and so on. I mean, I'm not a very good drawer, okay, but I hope you got the idea, okay? So program A, program B, or whatever program, programs use virtual memory address space, okay? In the virtual memory address space, with a maximum size of 4 gigabytes with a 32-bit memory space, okay? It runs sequentially. It feels like it runs sequentially. However, this is a virtual memory address space. When you actually run this, we need to copy this into the main memory, which we call loading, okay? But we cannot copy everything into the main memory. We need to put a little bit, because I have small RAM, okay? Whatever that I cannot put in the main memory, I put it in the swap space. And when I need that, I will just swap between main memory and swap space. That's why the name is swap space. And the part that's actually in the main memory, okay, it could be anywhere. It could be anywhere in the main memory. So, and I need to run in the real physical main memory. Okay? You might be confused at this point, but let me, explain more, and I hope that you understand this. Okay? So we're going to introduce a concept called virtual memory. Before this point, okay, everything that we've talked about so far was all in the virtual space, virtual memory space. It's not the real memory address. It's all virtual memory address, okay? And we're going to use the main memory as a cache. Here, this cache is not the cache that we've been talking about so far. The cache is a concept, okay? Cache is a concept. Like, my desk is a cache for my bookshelf. My bookshelf is a cache for the library, and so on, okay? So caching is a concept. We're using main memory as a cache for the secondary disk storage, okay? So CPU, main memory, disk, okay? And the main memory is like a cache of the disk. We do this to allow efficient and safe sharing of the memory among multiple programs. We're removing the programming burden of small, limited amount of main memory. What does this second line say? When I write code, I don't want to worry about whether my computer has 1 GB or 2 GB or 4 GB RAM. I just want to write my code, okay? I don't care, and it's still okay, okay? So going back here, let me actually just clear everything and redraw everything, okay? I might have a very small main memory. My main memory could be, let's just say 1 GB, okay? Okay? But I might write a program, program A, which uses 4 GB. I can write a program that uses 4 GB. That 4 GB program could be in your hard disk, 4 GB. This is program A, and I can still run this program. Okay, I can still run this program. I want to run this program, but when I run it, I cannot use the whole 4 GB, so I can just put a little bit here, maybe a little bit here, and then leave the other things in the swap space. Okay, I can still run a program that needs 4 GB on a computer which only has 1 GB. This is possible. How? Using virtual memory concept or virtual memory technique. Okay, so we remove the programming burden of having small, limited amount of main memory, and this virtual memory, this concept of virtual memory or this technique is managed jointly by the CPU hardware and the operating system. So now it's not just the hardware. Operating system has to help. Okay, and you will learn this in the operating system class next semester. Okay, when you take this operating system class, okay, this virtual memory is one of the most important things that you learn in that class. Okay, because the operating system must manage this virtual memory. Okay, so virtual memory is managed jointly by the CPU and the operating system. It removes the programming burden, and it allows efficient and safe sharing of memory across multiple programs. What do I mean by safe? What do I mean by this safe? Okay, let's go back here. Let's say I have another program. Okay, I have another program which, let's say, about this size, program B. Okay, I want to run program A and program B in my computer. Let me use green color for this. Okay, this is my program B. So program B was here. Okay, and I load it. I load it. Who does the loading? Who does the loading? This loading is done by operating system. Okay, your operating system will do the loading, and when it does the loading, it's going to make sure that this orange box and green box do not overlap. Okay, of course we don't want to do this. We don't want to do this. Okay, of course we don't want to do this. We need to make sure that this green box and orange box never ever overlap. Okay, and who manages this? The operating system. Your operating system will make sure that if you run multiple programs on your computer, you need to load that to the main memory. But when you load it to the main memory, it will make sure that they don't overlap in space. They don't, cross the memory space. Okay, this is what I mean by safe. Okay, your operating system must guarantee this so that you don't crash this program and that program, and you don't want any segmentation fault, memory corruption. You don't want any of that. Okay, so that's what I mean by safe. Programs share the main memory. Okay, each program gets a private virtual address space, virtual memory address space, holding its frequently used code and data and blah blah blah, everything that a program needs. Okay, and this virtual address space must be translated into the physical address space. Okay, we're talking about memory address, But virtual address space is a space on its own. It's space that I can use from 0 to 4 gigabytes. I can use anything there, but this is not the real address on the real memory. Okay? It has to get translated because I'm going to load it to somewhere in the real memory. Okay? This is real physical memory address. Okay? And this is virtual memory address. Okay? And these are protected from other programs. I just told you. Okay? The green boxes and the orange boxes, they should never overlap, and they should be protected from each other. Okay? So even if this green program uses, you know, this part, and the orange program, this is the orange program, uses this part, okay? These two might have same address in the virtual memory address space, okay? Might have same address in virtual memory space. Okay, so this part and this part might have same address in the virtual memory space, but when it gets translated, this will go to here and this will go to here, so they don't overlap. Okay, they are separated. This must be guaranteed, and this is done by the operating system, which you will learn next semester. Okay. So it's protected from other programs. This is how, you know, we make sure that one program does not overlap with other program. It allows a single program to exceed the size of the primary memory. I told you, okay? A single program can have up to 4 gigabytes on a 32-bit computer. A 32-bit computer, 32-bit memory address, 32-bit program can have up to 4 gigabytes of memory, okay? But your primary memory might be smaller than that. It might be 1 gigabyte, 2 gigabyte, whatever. Okay? You don't need to worry about that when you write a program. By the way, the difference between a 32-bit program and a 64-bit program, obviously, 32-bit program can use only up to 4 gigabyte. If you have a 64-bit program, you can use more than 4 gigabytes, right? Virtual memory automatically manages the 2 levels of memory hierarchy. 2 levels of memory hierarchy. What is it? The main memory and the disk. Okay, represented by, I wrote it here, main memory and storage disk, right? Okay. So if you think about it, let's go back this page. Okay, we have this problem number 1, sharing problem. Okay, this is solved by using this virtual memory concept. Also, we had the second problem. Okay, the difference between you know, how much memory your program wants and how much memory your actual computer has. Okay, both of these problems are solved using what? The virtual memory. All problems solved using virtual memory. Okay, I hope you got the idea. Okay, let me cut the video here and resume in the next video. See you in the next video. Bye-bye.